In exercise 2, we want to test if there is a relationship between gender and outdoor weekend preference, OWP. For the variable OWP, we consider two values, mountain and beach. In this table, we have the summary of the preferences as observed in our sample. It is always a good idea to write down the totals, 80 men and 120 women. 125 individuals preferred mountain and 75 individuals preferred beach. A grand total of 200 individuals. Letter A. Test if gender and outdoor weekend preference are independent by means of a chi-square test. The null hypothesis is gender and outdoor weekend preference are independent. In Chapter 5, Analyzing and Representing Relationships Between Categorical Variables, we studied the concept of probabilistic independence applied to events. A is probabilistically independent of B when the total probability of A equals the conditional probability of A given B, or equivalently, when the conditional probability of A given B equals the conditional probability of A given B complement. Now in Chapter 10, we are using these characterizations of independence. For the variables to be independent, the total probability of mountain must equal the probability of mountain given man, which must equal the probability of mountain given woman. The alternative hypothesis is that gender and OWP are dependent. That's to say, the total probability of mountain is different from the probability of mountain given man, which is different from the probability of mountain given woman. Since these two equalities are equivalent, either both are true or both are false. Also, here I am working with mountain. I could equivalently work with beach. Since beach is the complement of mountain, gender will be independent of mountain if and only if it is independent of beach. Finally, notice that dependent means the same as associated, while independent means the same as not associated. Later, I will speak in terms of association just for the sake of showing the alternative phrasing. The total probability of mountain observed in the sample is 125 out of 200, equals 0.625. I write this in red because it is a matter of fact. It is what we observed in the sample. Now we are going to create a new contingency table that is consistent with this table in the sense that the totals are the same, but which is also a direct translation from the null hypothesis. If we want the proportion of mountain among men to equal the total proportion of mountain, which is 0.625, how many men should prefer mountain? Obviously 0.625 times the total of men, that's to say 50. This 50 is the hypothesized number of men that should have preferred mountain. If we want the proportion of mountain among women to also equal 0.625, how many women should prefer mountain? 0.625 times the total of women, that's to say 75. Reasoning the same way, or simply subtracting from the total, we can get the amount of women and the amount of men that should have preferred beach. I write this in green because it is the expected consequence of the null hypothesis. This is the hypothetical table. Now we are going to apply the idea of goodness of fit to see how well our sample adheres to this hypothetical distribution. The total amount of deviation relative to the expectation equals observation of 60 minus expectation of 50 squared divided by the expectation, plus observation of 20 minus expectation of 30 squared divided by the expectation, plus observation of 65 minus expectation of 75 squared divided by the expectation, plus observation of 55 minus expectation of 45 squared divided by the expectation. All this equals 8.89. Is this much or little? Since the sample is random and the expected values are greater than or equal to 5, we can assume that this chi-square statistic follows a chi-square distribution with degrees of freedom number of rows minus 1 times number of columns minus 1, that is 1. What's the probability that a chi-square statistic is greater than or equal to 8.89 if we work with 1 degree of freedom? The table or the calculator will tell you 0.003. Therefore, this study provides strong evidence that outdoor weekend preference is associated to gender. The deviation from the hypothesized counts observed in the sample, chi-square with 1 degree of freedom equals 8.89, is statistically significant, p-value 0.003. This is the formula for the degrees of freedom of a chi-square distribution when we work with a contingency table. Letter B. Test if gender and outdoor weekend preference are independent by means of a C-test. The hypotheses are the same, although here I am using the alternative phrasing with association. Since the C-test is commonly used for proportions, let's use here the notation of proportions. Gender and OWP are not associated if the proportion among men equals the proportion among women, or equivalently, if the difference between both proportions equals 0. Let this denote always the proportion of mountain. The alternative hypothesis states that the proportions are not the same, so the difference is not 0. Gender and OWP are associated. If the null hypothesis is true, in the population there aren't 2 or 3 different proportions of mountain. There is only one, which is the same for men, for women, and in total. In that case, the best approximation that we can get from the sample is what we call the pooled proportion, the proportion in the combined sample. In the whole sample, we have a total of 125 individuals who prefer mountain, in a grand total of 200. So the best estimation of the proportion of mountain in the population is 0.625. We use this estimation to approximate the standard error of the sampling distribution of the difference between the sample proportions. We get an approximate standard error of 0.0699. We studied this formula in chapters 7 and 8. All this is hypothetical because it is built on the basis of the null hypothesis. The matter of fact is that in our sample there was a difference between the proportion of mountain among men and the proportion of mountain among women. This difference was 0.208. The p-value is the probability of observing as much difference as that, or even more difference than that, if it is true that the difference in the population is 0. We must multiply this by 2 because this is a two-tailed test. This probability happens to be 0.0015, multiplied by 2, 0.003, exactly the same p-value that we got in the chi-square test. The conclusion is equivalent. This study provides a strong evidence that mountain, and therefore outdoor weekend preference, is associated to gender. The difference of 0.208 observed in the sample is statistically significant, p-value 0.003. This exercise is just an example of the fact that the C-test is equivalent to the chi-square test for 2x2 contingency tables. Letter C. Is this a study about independence or homogeneity? This is the kind of distinction that many authors don't consider important in a course like this, an introductory course, but we still want to discuss it because it might be important in the future and also because some other authors make a big deal of it. A question is about homogeneity when we ask, is the distribution of a particular variable homogeneous throughout the different values of the other variable? In a question like this, one variable plays the role of the main variable of interest, and the other variable plays the role of a criteria to stratify the population in different categories. And the question is, does the variable of interest show the same proportion or the same mean in those different categories? In a question about independence, both variables play the same role, so to speak. We ask for both variables reciprocally. What happens is that in a population, this concept of homogeneity is mathematically equivalent to the concept of independence. That's why some statisticians don't pay much attention to the distinction. However, other statisticians do because it is looking at the question from two different perspectives. Many authors say that a study is more oriented towards independence if we select only one sample and for each individual in that sample we evaluate both variables, like we did here. For 200 individuals, we evaluated gender and outdoor weekend preference. These authors also say that a study is more oriented towards homogeneity when we select a sample from each category, and in these samples we evaluate the other variable. We did this in chapters 7 and 8. We picked one sample from the category of men, another sample from the category of women, and in these samples we evaluated, for instance, the variable approval-disapproval. The key difference between both sampling methods is that in the latter, the number of individuals from each category is selected beforehand. Here we wanted 1,000 men and 900 women. If we pick a single sample from the total population, we never know how many from each category are we going to get. For example, here we got many more women than men. But the fact is that with either of the sampling methods, we can infer about independence and about homogeneity. Here, even when we picked only one sample, we could infer that the distribution of mountain is not homogeneous throughout the different genders. Letter D. What's the main limitation of the chi-square test compared to the C-test? When do we use the chi-square test? The chi-square test is two-tailed. It only tests for different. The C-test can test for different, greater than or less than. However, the C-test is not available for contingency tables larger than 2 by 2. Then we use the chi-square test. The summary is that the chi-square test is used to test independence, homogeneity, and goodness of fit. We have already explained how related these three concepts are. Exercise 3 is an example of situation where we cannot apply the C-test because we have a 3 by 3 contingency table. We have three treatments, good wishes, bad wishes, and no wishes, and three outcomes, worsening, staying the same, and improving. The idea is trying to find scientific evidence of the existence of mental or spiritual powers. As we learned in Chapter 1, this is the type of study that should always be double-blinded and randomized. And here there is a comment. We always say that for these mathematical models to apply, the sample must be randomly selected from the population. In the case of an experiment, random assignment takes the role of random sampling. These 100 patients may not have been selected randomly from the population. Usually they volunteer and they have something in common. But the fact that they were randomly assigned to the different treatments allows us to use the chi-square model to test the possible association between the wishes and the recovery. Letter A. Does this study provide significant evidence of the existence of mental or spiritual powers? Use a chi-square test. It is always a good idea to begin by getting the totals. 20 patients received bad wishes, 50 didn't receive wishes, and 30 received good wishes. 29 patients in total worsened, 39 stayed the same, and 32 improved, in a grand total of 100. The null hypothesis is the equality, the statement of no effect. Wishes and recovery are not associated, or are independent if you prefer. The alternative hypothesis is wishes and recovery are associated. Something interesting is that among those who received bad wishes, more individuals worsened than improved, and among those who received good wishes, more individuals improved than worsened. Somebody could say that this clearly suggests that the wishes make the difference in the recovery. I could agree that these 4 values suggest so. The point is that if we just look at the part of the data that supports certain hypotheses, that hypothesis will always look like very supported. But what happens if we consider all these other values? Moreover, in situations like this, we don't want to compare observed values with observed values. We want to compare observed values with expected values. We must get all these expected values. When we do so, we notice that the differences are not too big. Here we got 8, we would expect 5.8. Here we got 6, we would expect 6.4. Here we got 10, we would expect 9.6. Here we got 7, we would expect 8.7. Notice that all the expected frequencies are greater than or equal to 5, which is a condition for the use of the chi-square model. But where do these expectations come from? According to the null hypothesis, the total probability of worsening should equal the probability of worsening given bad wishes, the probability of worsening given no wishes, and the probability of worsening given good wishes. This is the probabilistic concept of independence. By the way, it is also the concept of homogeneity. The outcome worsening is homogeneously distributed throughout the 3 treatments. The total probability of worsening is 29 out of 100. Therefore, among good wishes, we would expect 29% of the total of 30 to worsen. That's to say, 8.7. Among no wishes, we would expect 29% of the total of 50 to worsen. That is 14.5. Among bad wishes, we would expect 29% of the total of 20 to worsen. That is 5.8. The total probability of staying the same is 39 out of 100. Therefore, we calculate the 39% of the total in each category to get the expected number of those who stay the same in that category. And the same applies to improving. 32% among good wishes, 32% among no wishes, and 32% among bad wishes. Now we must apply the idea of goodness of fit. We must assess how well this observed distribution adheres to this hypothesized distribution. We get the statistic that measures the total amount of deviation relative to the expectation, what we call the chi-square stat. Observed value of 8 minus expected value of 5.8 squared divided by the expected value of 5.8 plus observed value of 14 minus expected value of 14.5 squared divided by the expected value of 14.5. We do the same with the other 7 boxes and we get a chi-square stat of 1.80. We know that this statistic follows a chi-square distribution with 4 degrees of freedom, the number of rows minus 1 times the number of columns minus 1. What's the probability of getting a chi-square statistic of 1.8 or greater than 1.8 if we work with 4 degrees of freedom? A table or a calculator will tell you that it is 0.773. This means that if recovery was independent of wishes, we would see deviations like this all the time, more than 3 out of 4 times. The conclusion is, no, this study does not provide significant evidence of the existence of mental or spiritual powers. The observed results are perfectly compatible with the hypothesis that recovery is independent of wishes. P-value 0.773.